So I'm just going to start by mentioning where we're going with what we're going to talk about today, because some of the topics will kind of seem like they're pieces of information and it's hard to see where we're going with it. So in chemistry, we like to know whether or not a reaction is going to actually go before we try it. That makes sense because you want to save your time and your money and your brains. And so we have a lot of little tricks to help us make reactions go, but what do you do, or how do you know if it's a reaction that is just never, ever, ever going to go regardless of what you do? So that's what this chapter is about. It's about predicting whether or not a reaction will happen spontaneously. That's what we call it, spontaneously. And there's a few things that matter. And so those are the things we're going to talk about first, separately, and then we're going to bring it all together when we talk about delta G. So the first thing is understanding this idea of spontaneity, or just this idea of deciding if something will ever happen. So if you take ice and you keep it at negative 10 degrees Celsius, this is just using your own knowledge. If you just keep it at that 10 degrees Celsius, what will the ice do? Well, it won't do anything, right? You know that if it's below freezing, it's just going to stay ice. You're not going to ever see at negative 10 degrees Celsius, and I'm assuming like normal pressure, right? You're not going to see it doing anything else. It's just going to sit there looking like a piece of ice, regardless of how long you're looking at it and observing it. At the same time, if you put it in an environment that's room temperature, so it's like this 25 degrees Celsius, if you put it in that environment, it's always going to be a liquid. It's not going to be, as time progresses, it's not going to stay ice. It's going to change into a liquid. And so that process of it changing into a liquid, that is spontaneous. There's a letter that you'll learn about. It is delta G. That's the letter we use to describe this spontaneousness. Now, what I just was describing was a phase change. It wasn't a reaction, but it's a nice place to start because we'll look at phase changes as well as reactions, and whether or not certain phase changes at temperatures are spontaneous or not. And so this kind of like pulling back in the idea from an earlier chapter when we were talking about phase changes and at what temperatures and pressures they happened at. So then will it reverse? If you're sitting at 25 degrees and you don't change it, will the ice ever turn back? Will the liquid water ever turn back into ice? And no, it's not going to reverse. The only way to reverse it is to change the scenario, take out heat, and then it'll go, right? So just sitting there of its own accord is not going to do anything. Now here's another situation, and this situation is for the reaction. So I've got some cars here. And if you didn't know, iron is like that. Under the car layer, you've got iron somewhere on your car, even though I know they use a lot of other materials and plastic nowadays too. But if iron is exposed to oxygen and for long enough, you're going to end up with rust. So this person has a painted car, and as it's sitting outside, and if they don't do anything, and this is over a period of time, right? It's not immediate. So something doesn't have to be immediate to be a spontaneous reaction. It just has to eventually happen. Then your unpainted, scratched up surface of the car will eventually develop rust all in it. Is that reversible? No, you clean off that rust. You actually are scraping off a layer of your car. It's not like you're turning that rust back into the iron. So those are both spontaneous processes. They don't have to be immediate. They just have to happen. They have to go. They have to do something. So there are two driving forces, and one of them you've actually already seen before, and it is enthalpy. And I like to write enthalpy, all enthalpy, like that. And I like to set it on fire. So here's our enthalpy on fire. And I like to do it that way because that gives me that visual to remind me that this is talking about heat, energy. And then I like to write the word entropy, which is the other thing. And you haven't talked about this, but entropy. I like to write it like that because it looks like disorder. So these are the two things that will be talked about. We're going to review some enthalpy, and then we're going to look at what is entropy, what is disorder. And the two symbols for these, you've got an H for that one, and you have an S for this one.